Okay, thank you. Welcome back, everyone. I see our coffee line's got a lot shorter. I'd like to introduce our next speaker, Bryan Catanzaro. I've known him for over a decade, almost 2 decades now, and he's an exceptional researcher and exceptional engineer. Bryan is a vice president of applied deep learning at NVIDIA, where he helps lead the Nemotron team that builds NVIDIA's open foundation models. Bryan helped create cuDNN, which many people here have probably used, and that was NVIDIA's first AI product. And he's worked on DLSS, the most widely deployed neural rendering system, which uses AI to make graphics more compute efficient, 10x more computer efficient. And Megatron, which set speed records at scale for training large language models and forms the technical basis for many generative AI projects around the industry. Bryan is a strong advocate for open source science, and his team contributes models, data sets, and techniques through Nemotron to ensure developers everywhere can build, customize, and safely deploy AI. With more than 45,000 academic citations, his research spans deep learning, computer graphics, large-scale systems, and Bryan received his PhD in electrical engineering and computer sciences from the University of California, Berkeley. My last pitch is, I recently bought a Nintendo Switch 2 for my kids, and it works so well thanks to Bryan and the work that he's been doing there with accelerating computer graphics. Thank you so much for joining us today, Bryan.
Thank you. Thank you. I'm really honored to be here. Thanks for inviting me. And I didn't plan on saying anything about the Nintendo Switch 2, but just because you mentioned it, it's kind of a crazy idea that you could make graphics, which is one of the most computationally intensive workloads that humankind has ever run into. It's kind of a crazy idea that you could take that and make it more efficient by adding AI inference to it. Because AI inference is expensive, right? It takes a lot of work to run an AI model. And if you're trying to generate a video, high-resolution video in real time using inference, how is that going to make it faster? It's been a great honor to work on that project and know that AI is now making graphics around the world an order of magnitude more power efficient, because it turns out there's a lot of correlations in videos that you can learn with a model, and then instead of actually running programs to compute every color of every pixel, you can just infer it. It's much cheaper. This is the kind of work that we love to do at NVIDIA. We love to think about a problem from first principles and reason about, what are we actually trying to do, and then figure out how we can bring the ideas behind accelerated computing to solve that problem in a different way, a better way. This is why NVIDIA has been able to contribute to the development of systems for AI in the way that it has over the past 2 decades, is because we're not just building systems, we're trying to think about the underlying problem that the systems are trying to solve. We're trying to understand that deeply and then accelerate it. And sometimes the way we accelerate it is by inventing new algorithms like DLSS. That's kind of an intro to what I'm going to be talking about today, which is what we're doing in the broader AI space with large language models, and we call that Nemotron. Now, fun fact, Nemotron is actually a portmanteau. It's actually 2 names that got mashed together. The first name is NEMO, which is also a portmanteau. It stands for Neural Modules. The idea behind the Neural Modules or NEMO project was it's really hard to build AI systems that work, and they need to be composed. There needs to be all these sort of different pieces that compose together. We want to make that easier so that enterprises can build and deploy AI. And that project's been going on for quite a while and is used by a lot of companies around the world. Well, the NEMO team was busy building basically software to help companies build AI. Meanwhile, we had the team that I was involved with called Megatron. Megatron, if any of you guys have watched the Transformers, is the biggest, baddest transformer. And so the Megatron project was all about how do we train and deploy the biggest transformers at scale. That project started a long, long time ago. Because we needed to actually test our software, right? It's no good if you say, hey, I've got a system that's really fast at training a neural network if you don't actually train it, because how do you know if it's any good, right? And there's lots of ways to say that something's fast that actually get bad results when you try to use the model. So because of that, NVIDIA invested in compute for itself so that those of us working on Megatron systems could actually train models to make sure that our software that we were developing to show the scalability of NVIDIA's systems actually yielded models that were useful and good. And so we had the NeMo team, and it's trying to help enterprises build and use AI, and we had the Megatron team, which is trying to show how to use NVIDIA systems to build AI, and we decided to work together, and that's where the name Nemotron came from. That plus, I think also, like, Megatron was too scary for corporate people because he was the evil one, and we didn't want AI to be evil, which is good. That's good. So that's what I'm going to be talking about today is what NVIDIA is doing to try to build an open and accelerated future for AI. Now, NVIDIA believes that AI is not one size fits all. We believe that we need a lot of different kinds of models. A lot of different sizes of models, systems of models. With GPT-5, one of its features is that it has a router that sends your request to maybe a collection of models, depending on what it judges the complexity to be. And that's one example. I think there's going to be other kinds of specializations for these models. We know that solving a problem is not just about raw intelligence. It's also about positioning and access. What do I mean by that? Well, I think of intelligence as raw material. It's like horsepower of an engine. If you have an engine with more horsepower, it can, in theory, do more. But an engine by itself doesn't do any useful work. It needs to be hooked into a system that's actually doing something. And when we think about the systems that people are building to use and deploy AI, we know that they're quite diverse. There's a lot of different kinds of problems that different industries face. And we also know that the ability of any sort of intelligence to solve a problem critically depends on the data that it has access to. And we know that the world's most valuable and sensitive data is always the hardest to get access to for good reason, right? Privacy is essential. Every business is built around a secret. There's some sort of secret that every business needs to work with in order to bring its unique perspective to solve its problems. And so because of that, we believe that specialization is really important. And we believe that, we would like to support the development of lots of different kinds of AIs, small ones, big ones, in all sorts of different areas. Now, the third part that we're thinking about always at NVIDIA is about efficiency. And when we started the Megatron project back in 2018, it was all about pre-training, right? And just trying to train a large language model on all the internet, that was a really difficult computational problem. But then, ChatGPT came along, and people realized post-training with reinforcement learning is actually really important. It's a really important way of making models useful for problem solving. But that adds another dimension of compute and another compute problem. One of the things about reinforcement learning for post-training that's very interesting computationally is that, as the methods get better, the compute demands increase because the model is essentially starting to teach itself how to solve problems, with things along the lines of self-play. So, and it's also a more diverse problem computationally because you're doing both training and inference at the same time. And you might say, well, why is inference different than training? It is actually computationally really different. And so you need to think about, like, how do we build a system and how do we accelerate that? And then, now we have a third wave of compute scaling, which has to do with thinking at deployment. So when a model is trying to solve a problem, a problem has been posed to it, it now has the ability to spend some time thinking and reflecting and hopefully using that time to come up with a better answer. And so we look at all this together, and it's an amazing challenge to support the industry as we move in this direction. And we believe that because of all that, AI isn't a one-size-fits-all problem. So to try to address this, we have this program called Nemotron. Now, Nemotron has a bunch of different things. It does have models, which I'm going to be talking about a little bit today. And in the future, I expect NVIDIA to continue to release these models. And I'm really excited about what we're training right now. I think there's some really cool things right now burning up a lot of GPUs around the world for Nemotron. But Nemotron is not just a model. And the reason for that is that NVIDIA is a different kind of AI company. NVIDIA is supporting the industry. We don't actually deploy the AI ourselves. We support businesses around the world as they deploy their AI. And so in order to support that, we are making Nemotron absolutely as open as possible. We release not just the models, but also the data sets that we use to train the models, including the pre-training data sets, which is pretty unusual. We release all of the numerical techniques and recipes. When I look at the way that we're spending our compute budget at NVIDIA to build Nemotron, a large amount of it is actually doing ablation studies and scaling law studies, trying to figure out how to mix data together, what kinds of learning rates, schedules we should use, and so forth. These sorts of things are not very deep. Like technically, this is we're just trying to figure out what the right hyperparameters are. But on the other hand, it's really expensive to do it, and the answers have a big impact. So we release everything that we learn through this process as part of Nemotron. It also includes our software. So we have a lot of software that we're building to support AI, libraries of different kinds, and of course the research that goes into it, which I'll be talking about a little bit today. Now, why is NVIDIA doing Nemotron? Like, why would it make sense for NVIDIA to do this thing? This is an expensive thing. Nemotron is a big commitment. It's a lot of GPUs. And it's one of the hardest things about my job that every GPU that I get to use for Nemotron is a GPU that we didn't get to sell to somebody else. And so the salespeople are always looking at it with a jaundiced eye, like, wait, does Nemotron really need to exist? We could sell that, there's really two important purposes that Nemotron serves. And the first is to help NVIDIA build its core products. So I started out this talk discussing DLSS and how our thoughts about how AI could transform graphics have radically changed the systems that we build for graphics. These days, graphics workloads are primarily running DLSS, and the more that graphics becomes an AI problem, the different the system is for doing graphics, right? The same is true for AI, There's critical questions that we need to know answers to in order to design systems for the future. Things about how do the interconnects work? What kinds of numerical precision and sparsity should we use? And things like, for example, diffusion models versus mixture of experts models versus hybrid state space models. All of these things have an enormous impact on the kinds of systems that we should build. And so in order to answer those questions, we need to train models, and we need to know all of the details that go into that. One just example of this recently, last month we released a paper and a blog post describing how to use 4-bit weights to train large-scale language models. And first of all, let's think about that for a second. How crazy is that, right? 4 bits, that's only like 16 numbers per parameter, right? How are you gonna train a model and get the same results as a model with thousands of possibilities per parameter? Well, it turns out it's not just 4 bits per parameter. There's also blocks. There's a hierarchical system of scaling factors that are hardware accelerated in our Blackwell generation. And then there's a bunch of numerical algorithms that we've developed in order to stabilize the training process and make sure that we're not running into underflows and overflows as we deal with these very restricted numbers. For example, we we have inserted randomized Hadamard transforms into all of the quantization of all of these layers. The purpose of the Hadamard transform is it's a numerically reversible technique that smushes outliers around, so that like all of the energy from your outlier numbers get distributed over a block of numbers. But the crazy thing is that it's reversible, so that then, after you store it in this 4-bit format, you can undo it and then, recover, the original numbers back. So there's a lot of sophistication that goes into those algorithms. And at the end of the day, what we're trying to do is make language model training dramatically more energy efficient. If we can use only 4 bits per parameter instead of 8 or 16, then that should reduce the cost in watts that it takes to train a model, or joules, sorry. And if we can do that, then of course AI will get stronger. The more efficient that we make the systems for AI, the stronger AI gets. That's been true for decades, and it's something that really drives our work at NVIDIA. So, we would not have been able to develop these 4-bit training algorithms without building Nemotron. And we know that by showing our customers what's possible, how to accelerate AI, that they're going to get better results, and AI as a field is going to develop. And that's going to be a great opportunity for us. So that's the first reason why we build Nemotron, is that we have to in order to support our main business. Now, the second reason why we build Nemotron is because we want to accelerate the ecosystem. We know at NVIDIA that whenever AI grows, it's an opportunity for us. And we know that there's lots of organizations around the world that would like to build their own AI in different ways. And that it's difficult to do that. So if we are building Nemotron and we can contribute that to an open source community, and hopefully by doing so inject more vitality into open source AI, we think that would be a really great thing for our future. And so those are the 2 main reasons why we're building Nemotron. There's kind of 3 main ideas behind Nemotron that we're trying to make it, kind of inform our approach to building it. The first is that, we're an accelerated computing company. We come to AI from the position that speed is the fundamental problem in AI. And many people can disagree with that. That's maybe a controversial position. But if you work at NVIDIA, everybody breathes speed. It's like we just have to make it faster. And so we have this belief that faster AI is smarter AI. Well, why would that be true? Well, earlier I was talking about the 3 different phases of building AI. There was pre-training, there was post-training, and there was test time thinking. And during each of those phases, if you're faster, you can learn more. During pre-training, if you're faster, you can train on more data, you can train a bigger model. During post-training, using reinforcement learning, if you're able to think faster, you can actually go through a lot more rounds of reinforcement learning, and the model just gets better for every round. So you can afford to do, it's basically like you got a scholarship to college, the cost of college just went down by a factor of 10. You can, really get a lot more learning done. And then, at test time, when the model's deployed, if the model's faster, then, given any time constraint that a business or an individual might face, you're actually able to get more cycles of thinking done. You can get to a better answer. So, so we have this fundamental belief that speed connects directly to intelligence. Now, we are also building Nemotron to run on big production systems. We're thinking about, what is a computer? To NVIDIA, the most important computer is a data center. It has many thousand GPUs. It has crazy interconnect. We've been talking about our NVL systems, where we have 72 Blackwell GPUs today that are all interconnected as one. They can all read and write each other's memory coherently, really, really fast. And then we have, that's like one rack is like 72 GPUs in a rack, and then we have many racks in a data center. We're thinking about, we're distributing AI workloads across these big AI factories that are generating tokens, and we want to make those as efficient as possible, because we know that that's going to make AI more deployable if it can be cheaper. And so, so that's kind of our second axiom is that we want to aim for these big, huge systems and keep them fully loaded. And then the third thing is we're trying to co-design Nemotron with accelerated systems in mind. So particular systems, like as we build, right now we have our Blackwell generation, and in our next generation will be Rubin. We're trying to connect the ways that the systems that we're building are designed and their features. We're trying to connect that with the way that Nemotron models are architected and take advantage of all of that. Okay, so I wanted to talk about open source a little bit for AI. I guess the reason why I wanted to show this slide is because over the years, there's been a few organizations that said that they really believed in open development of AI. One of them was called OpenAI. I don't know if you remember that one. Sorry. I love OpenAI, by the way. Like, I'm not trying to be too salty here, but like, it is difficult to speak about OpenAI technologies without saying the word OpenAI, but it's not. It's difficult, you know what I'm saying? So, so there's been a lot of organizations over the years that have said that they really want to build open technologies for artificial intelligence, but each of them has kind of run into what I would consider a business limitation, because it turns out that in order for their business engine to work, they needed to deploy it themselves, and they needed to sort of monetize the deployment of AI. Now, NVIDIA is a different kind of AI company, right? As I've been saying, we don't actually deploy the AI ourselves. We support other people who do. And that means that our opportunity is not connected to how it's deployed, but we can just support the industry. And so for that reason, I think NVIDIA is able to be much more committed to open source. I expect you're going to see quite a bit more commitment from NVIDIA in this direction. Because it's in our interest, because it helps us build systems and because it helps us grow the community, and ultimately that's good for NVIDIA. Now, we've done a lot of things over the years. Megatron I've been talking about back in 2018. We released it in 2019. We built a bunch of Megatron models over the years. One thing that I am really proud of is our in 2021, it's not on the slide, but we trained a 530 billion parameter model jointly with Microsoft. And that model was a good model for its time. But what I'm proud of is that we did it in conjunction with Microsoft. And a lot of Nemotron has been done in conjunction with other companies. So for example, we built Mistral Nemo in collaboration with Mistral. We've built a collection of Llama Nemotron models, building off the excellent work that Meta has been doing. That sort of supportive orientation, Nemotron is not just a model. Nemotron is our AI technology. It can be applied in a lot of ways, and it can be applied in conjunction with others, and that makes us happy. We are very happy, for example, when we release technologies as part of Nemotron and then other people use them and improve upon them. That's a success for Nemotron. That's, and I think that makes Nemotron special, and it also makes our commitment to open source more enduring. And that's, I believe that's going to hold going forward. So I want to talk a little bit about what we're up to in Nemotron today. Right now, our most recent models that we released, we have a Llama Nemotron Super, which is a 49 billion parameter model. We have Nemotron Nano version 2, which is a 9 billion parameter model. This is the artificial intelligence index, and if you look at the bright green bars, you can see that Llama Nemotron Super is doing really well for a 49 billion parameter model. That was built off of Llama 3.3, which was not a reasoning model, so we added Nemotron reasoning technology to Llama 3.3 and got a pretty decent model out of it. And now we also have Nemotron Nano V2, this 9 billion parameter model, which we released a few months ago. It's in artificial analysis's index, it's on par with QN3 32B, but it's about 20 times faster. So we're excited about that. Obviously, the next question is, well, when are you going to make bigger ones? And stay tuned. Let's talk about Nemotron Nano V2. That's the one we released most recently. It's actually not a pure transformer model. It's what's called a hybrid state space model. It's using the Mamba 2 state space layer. You can think of state space models as kind of like, I don't want to like make people angry, but like kind of like a recurrent neural network, you know. So there's a recurrence. There's a way of reasoning about a sequence of data that is not full global attention. Now, the global attention in transformers is really powerful. It lets the model direct its attention to the entire sequence at will, many, many times, because there's many layers, right? And there's many channels. And so the model has a lot of capacity to inspect the sequence forward and backward and all the other ways. The problem with it is that it's a quadratic algorithm, and it takes a lot of memory to hold all of those activations. We call that the KV cache. Now, because the memory is so large for all those activations for that quadratic problem, that often limits the batch size that you can deploy a model at. And running at a lower batch size makes the GPU less efficient. And so when we're thinking about how do we make something faster, this is one of the obvious things to do is let's try to make attention more efficient. Let's try to use less of this quadratic algorithm and use less memory. And so that's what we've been able to do with this Mamba 2. Now, in this model, about 8% of the layers are still traditional full attention from a transformer. And we found that that's really helpful. You know, going to 0% we found is a bad idea. But with this hybrid architecture, we find that having just a few layers that have the ability to do global attention across the whole sequence is enough. And then the rest of the reasoning about the sequence can actually be done through this linear algorithm with the state space model. And that actually gives us a more accurate result, and it's much faster. So how does that look? You know, for a given amount of inference, Nemotron is smarter. That's what we're trying to do. We actually built Nemotron Nano V2 with a controllable inference budget. So the amount of tokens that the model is able to spend thinking is a parameter that we can tell it at inference time. And basically what it looks like is the inference procedure, you know, let's say we're going to give it 10,000 tokens of thinking. The inference procedure is watching the model once it goes into think mode. And then after 10,000 tokens, then the inference procedure tells the model, hey, time to wrap it up, and gives the model just a little bit of a grace period to finish its thought. If the model doesn't emit the end think token and just keeps rambling on, then the inference procedure just like cuts it off. Anyway, so it's a fairly straightforward technique, but the result is that we can control for how many seconds is the model thinking. So here's 4 different benchmarks comparing this 9B model against QN3 8B. And you can see that like and the x-axis is a log scale, right? So you know, as we give the model more time to think, it gets more accurate. It's able to solve problems better. But you know, for any given amount of time, the Nemotron model is faster. We see about 1.5 to 6 times speed up, especially at long context use cases and at high concurrency. And you know, recently we just released an FP4 checkpoint to take advantage of the Blackwell FP4 acceleration, which we're excited about. Okay, but you know, along with this model, we didn't just release a checkpoint. We also released all of our pre-training and post-training data sets so that anybody that wants to build an AI can use these data sets and build their own. And you know, I wanted to highlight 4 of the pre-training data sets that we released. There's about almost 7 trillion tokens of filtered and rephrased data that we released. And you know, when we think about the compute that's going into Nemotron, actually the majority of compute is going into things like rephrasing our data set, not just training the model, right? So it's actually quite a lot of work to put these data sets together. So we have this is our second release of Nemotron Common Crawl, where Common Crawl is this thing that, you know, anybody can use to download snapshots of the internet. But then we've taken all that data, we've deduplicated it, we've filtered it, removed things that, you know, were just going to be confusing for the model, and then we've rewritten it, you know, especially for things that help the model gain more intelligence. You know, you can imagine like just if you want a model to be good at solving math tests, maybe find all the math tests on the internet and then rewrite them in a bunch of different ways so now you have more math tests to show the model. Or maybe rewrite them in different languages, right? So that the model learns how to understand and how to output in multiple languages. We also have a math data set. I'll talk about that a little bit in just a second. And we have a code data set where we downloaded a lot of code from GitHub. And then we have a synthetically generated data set that's it's part of our supervised fine-tuning. So this is kind of getting into post-training. Post-training usually has supervised fine-tuning as the first stage. But we use some of that supervised fine-tuning data set in our pre-training because we find it makes the model better. I'll be talking about that in a second as well. Okay, so about the math data set, I thought this was kind of fun. Some researchers had the idea that if you look at Common Crawl, there's a lot of math on the internet, but it's actually really hard to extract it from the text of the web pages because it comes in really different forms. So there is LaTeX in different ways. There's a lot of different ways to write LaTeX inside of a web page. There's image tags. So there's this like website that like, if you look in the pink box, it's like, here's a LaTeX equation that you give it to this website, and then it will render an image for you of an equation. There's MathML, there's XML tags, there's a whole bunch of different ways of writing equations. And so what we did is we actually used Lynx, which is a text-based web browser, to render all these web pages, and then we use another LLM to extract all of the math from all of these web pages that have been rendered with Lynx, and then we use that to build this math data set. So I thought that was pretty fun. And again, we're, sorry, pressing the wrong button. We've released that as part of this effort. So Nemotron is not just a model. Models are part of it, but it's also got a lot of other things: data sets, techniques, numerical recipes. By releasing all of it in an open way, we hope to support the development of AI around the industry. Okay, now I wanted to talk about systems for a little bit. So these days, Blackwell is our most recent GPU architecture. And fun fact, it's named after Professor Blackwell from UC Berkeley, who was a mathematician who developed a lot of important techniques for statistics. And I always forget, is it David Harold Blackwell or Harold David Blackwell? I forget, and I always say it the wrong way, but it's one of those. Now, as a proud Berkeley alumnus, I have to say go Bears, and also Stanford doesn't have a GPU yet. Like, there's not a single GPU that's named after a Stanford scientist that I'm aware of, and long may that continue, as far as I'm concerned. When we take these Blackwell GPUs, they're hooked up into these big racks, right, with NVL72. So there's 72 GPUs, there's 576 memory chips, there's 18 NVLink switches, 130 trillion transistors, about 2,600 Grace CPU cores, Grace being named after Grace Hopper, the admiral that invented compilers. We have also the networking, the NICs, and the DPUs that hook this all up. And so it's a whole rack. It's very tightly integrated, and that's the systems that we're currently selling. Why did we build this? Why did we build this system? Well, it's really for inference at scale. You know, inference is the way that AI, where the rubber meets the road. It's where AI gets deployed. And what we're trying to do is push out the Pareto frontier in terms of efficiency and interactivity. So, if you think about it on the x-axis here, we have tokens per second for a single user. And this corresponds to sort of the fluidity, the iteration cycle time that an individual has when they're working with an AI. And we want that to be as fast as possible. So we want the tokens per second per user to be as high as possible. That's the x-axis. Now, the y-axis is tokens per second per factory, right? So we have this expensive building full of computers that's running this inference procedure. We want that to be really efficient because obviously that's how you get ROI, right? Now, it turns out that these things are in opposition to each other, as you might expect. As you make inference faster for one user, it's going to slow down the other users because you're spending all of your compute just to try to do one thing as quick as possible. So that's kind of on the right-hand side of this graph, and on the left-hand side is where each user is getting a really slow response, but the factory is very efficient. So in this cartoon here, the sort of bright region, we kind of think about that as like the sweet spot, where we're trying to get both very high single user interactivity as well as very high overall factory efficiency. What we're trying to do is move that Pareto frontier up and to the right. And the way we do that is with all of this thing that we call accelerated computing. Of course, there's flops, there's memory, there's HBM, the bandwidth of the memory, there's the software and the algorithms. All that is trying to move this. So let's look at an example. So this is comparing Blackwell against Hopper. So Hopper, again, named after Grace Hopper, the pioneering admiral of compilers. And if you look at what we were able to do, I think this is for the DeepSeek model that came out last year. We get this curve, right? The maximum throughput we can do for a single user is somewhere around 250 tokens per second. The maximum throughput per megawatt that we can get is somewhere around 2.5 million. Okay, now with Blackwell, we have a bunch of technologies trying to make this better. We have 8-way NVLink, and we have, let's say we're using FP8 numerics in Blackwell. That has an advantage because of better interconnect and faster GPU, but it's basically just similar kind of inference to Hopper, just with the next generation. But then we use FP4 numerics. I was talking about that we have a special 4-bit numerics format in Blackwell. That moves it out a little bit more. And then we have NVL72, and it turns out that using a bunch of GPUs together can dramatically push that Pareto frontier out. And then we have Dynamo, which is a software library that we've built that thinks about all of the different ways of parallelizing the inference compute across a factory, across racks and racks of GPUs. And that is able to actually find some solutions, some different ways of running inference that move this curve out even further. And if you look at the area under the curve, that's what this cartoon is really doing. Using all of these things together, all these technologies, including Dynamo, we're about 25 times more efficient at 1K token input sequence length and 2K output sequence length. And if you look at this rainbow of different things, what these are showing is different forms of parallelism, right? So the top one says expert parallelism at 8. So we're doing 8-way expert parallelism, which is a technique for serving a mixture of experts models with a batch size of 3072. And we've turned disaggregated serving off. Disaggregated serving is about treating the input sequence and the output sequence differently, because the input sequence tends to be compute bound. You're able to just process the whole thing through the neural network all at once, whereas the output sequence for every token, it tends to be memory bandwidth bound, because you have to finish all of the work to stick one token through the model, and then you take that output and you stick it into the beginning of the network and do it again. And that means that there's a lot less math per weight as you're streaming in the weights from memory. It tends to be more bandwidth bound. So disaggregated serving is a way of taking advantage of that so that you can actually get more efficiency if you play your cards right. But it turns out, if all you're doing is trying to make the factory as efficient as possible, you don't need disaggregated serving. But then, in blue, we start turning on disaggregated serving in order to increase interactivity and push this curve out. So this is accelerated computing. This is what NVIDIA is trying to do. And we can get to 40x at different, this is a case where we have a lot bigger input sequence length, so we're trying to read more context through the model. That can be even faster. Now, I've been talking about accelerated computing this whole time and saying Nemotron is a really fundamental part of how NVIDIA is thinking about accelerated computing going forward, but I just wanted to kind of reiterate that just a bit. What is accelerated computing? And actually, accelerated computing, if you think about it, is actually decelerated computing. Why would I say that? Well, it's not a new idea that computers should be fast, right? NVIDIA is not like a unique company or nobody in the computing industry would be surprised if you said, well, I'd like to make a fast computer. People would be surprised if you'd said you wanted to make a slow computer. Why would you want to do that, right? So making a computer fast, saying I want to accelerate a computer, actually, that's kind of a vacuous statement unless you are thinking about specialization. If you're thinking about how am I going to make this computer especially good at something that really matters, and in the process, I'm going to slow down everything else. That's how accelerated computing works. It's really about specialization. But that means that if you want to work in this field and do accelerated computing, you have to know a lot about what you're trying to accelerate. If you guess wrong, if you build a system to accelerate the wrong thing, it's not going to be worthwhile. One of the things that's different about accelerated computing versus just standard computing tends to be about, I'm going to sell you a computer. The computer is going to have this many floating point operations per second in it. It's going to take this many watts to run. It's about a thing that you build. But accelerated computing is really about time and capability. It's really about, I want to build a system that enables an engineer and a scientist to do something that they couldn't do with a standard computer. But what that means is that all of it has to work, right? There's a chain of like 100 interlocking technologies ranging all the way from algorithms down to transistors and everything in the middle. All the software, all the compilers, libraries, frameworks, the makeup of the GPU, the interconnects and the CPUs, and the algorithms, all of that, all of them have to contribute to the acceleration. If any one of them is a weak link in this chain and slows it down, then people don't get the ability to do something new with that computer, and therefore it's worthless. So the value of accelerated computing is really high because the value of time is really high. But it's a challenging problem because it all has to be accelerated, and in order to do that, you have to understand the problem computationally from first principles. You have to understand it top to bottom. These days, we continue to advance the GPU. It's the heart of NVIDIA, and I think it always will be. But when we look at some of the most exciting speed-ups that I just showed you as we walked through the Blackwell GPU, a lot of it was coming from interconnects, like NVL, numerics. So you saw a big benefit from FP4 numerics. But of course, you can't just like randomly decide to use a different data type and hope that it's faster, so it's good. No, it actually has to be good, right? If you make it faster by using worse numbers, worse arithmetic, but the results are bad, nobody's going to use that. So this is accelerated computing, right? So like we have to know about numerics, we have to know about sparse algorithms. Neural net architectures, right? So like I was talking about how hybrid SSMs have really been able to accelerate Nemotron. Mixture of experts, also a really powerful tool for accelerating neural nets. Training data sets, we released our Nemotron Common Crawl data set for pre-training, and we didn't release our version 0 of that. But if you compare our version 0 versus our version 1, our pre-training sped up by a factor of 4 because the data set was smarter. That had nothing to do with the numerics or the GPU. That was just, if you look during the pre-training process at how quickly the model's learning, it's learning 4 times faster because our pre-training data set was higher quality. And so what that implies is that actually pre-training data sets are now part of our accelerated computing problem, right? If you have a bad pre-training data set, you don't get the time, you don't get the capability, you don't get the value ultimately. So that's why accelerated computing is so much more than a chip. Optimizers, optimization algorithms, also really important. And a new one that I've been thinking about a lot has to do with brevity. So I was showing you this plot of like, we want to get the most tokens per megawatt out of a building. That's true, but like, how much information is in a token? If your language model is really verbose, if it just goes and goes and goes without really providing much information or ideas, then that's going to slow you down, right? So it's not just tokens per megawatt, it's actually like problems solved per megawatt. And that means that you have to think about the succinctness of the outputs of your neural network as an essential part of accelerating the system. So this is the challenge of accelerated computing, and that's why we're building Nemotron, why we have to for our fundamental business. And anyway, I wanted to give you all of that context because I think it's important. Like when you think about like why would you believe me when I say that NVIDIA has a pretty big commitment to building Nemotron and building it openly? Because I'm trying to explain to you how it's in our interest, how we need Nemotron in order to do our work, and how we also believe that the community needs Nemotron in order to grow and flourish. We need more diversity. We believe AI needs to be as diverse as the people deploying it. And we also think that trusting AI, it's much easier to trust an AI if you can inspect how it was built and understand everything that went into it. And so we think that's important for the future of AI. Just wrapping up, what is Nemotron? We're trying to accelerate AI. We've been doing that for a long time, but Nemotron is a new vehicle for us, or maybe not new, but a vehicle that maybe you haven't heard about that we're trying to tell you about. That's really important to us. That's going to help us bring AI to the next level. We hope that we're going to be able to do that in conjunction with many of you. That's why we're releasing it in an open way. We want to encourage the development of AI in all sorts of different new ways, different ideas, different applications. We want it to be tightly integrated into the beating heart of every business. And we think by providing all of this technology to the community, and also we can learn from the community, from you guys, from others, from the great ideas that are out there, that we can help AI grow, and that's how we're going to move to the next level. So with that, I'd just like to say thanks for having me today. Do we have any time for Q&A, or should we just wrap up? Okay, great, awesome. Anybody got a question? Somebody going to run mics around? This guy raised his hand first.
Hello, thank you for the awesome talk. I want to ask about how closely do you all work with the compiler folks of like, let's say JAX or PyTorch, et cetera, because your team designs the hardware and they want to design the compiler that talks to the hardware.
Absolutely, yeah. Compilers are such an essential part of this entire stack. There would be no way that we could accelerate AI without really investing in compilers. So it's something that we continue to work with. JAX and PyTorch, are near and dear to our heart. Also MLX, I know there's going to be a talk about MLX. NVIDIA loves MLX. We're really happy to work with frameworks and compilers around the industry to try to make them faster. Because we see that as an essential part of accelerated computing. Yeah.
Hi, so I had a question. So around last year, like in May, NVIDIA chose to ban a conversion layer of CUDA. It's called Zulda. And so my question is that you talk about being dedicated to open source AI, and I think that's great. I mean, imagine if we had a company that had open AI. That would be like crazy, but sadly we don't have that. And so my question is like, how do you bridge those two? Like on one hand, you have these decisions made by NVIDIA that seem to basically be protecting CUDA at all costs. And on the other hand, you're releasing these models that are like open source, but in the end, they all rely on CUDA and NVCC, and without them, like you can't really like run it on customized hardware that's made by different people.
I'm not familiar with the specifics of Zulda, but NVIDIA does not ban applications of CUDA. CUDA, anybody can write CUDA programs. It may be that NVIDIA didn't choose to put a lot of energy into putting its own engineers to make that project better. I don't know, but certainly NVIDIA wants to support the development of AI. We believe that when AI grows, it's an opportunity for us. And we also, have a business that's built around making and selling systems. Every business has, the way that it accesses its market, and that's the way that we access ours. So, I think openness is a thing that, every company works with in a different way. I think what we're doing with Nemotron is a unique way of building AI in the open. We hope it helps the community.
Thank you so much.
Oh, okay, great.
So hopefully we'll be able to catch up with Bryan over lunch and ask more questions.